Hello everyone! Today we will continue with support vector machines. Last time we have introduced support vector classifiers starting from maximum margin classifiers. Support vector machines has a well-established literature and are one of the most popular machine learning methods in practice. So far we have covered quite a number of machine learning models including decision trees and random forest, which is a well-used method in machine learning area. We learned the theory behind the methods and also their work in practice. You can see those videos using the link above. Let us start. Let us first recall what the support vector classifier is. Remember that in maximal margin classifier, we are looking for the best separating hyperplane. That hyperplane is heavily depending on the dataset as expected. However, a small change in the dataset would cause a completely different separating hyperplane. And this is not what we want. We want to have something more robust to this kind of changes. As you remember, support vector classifiers are used for this aim. They provide more robust solutions for the observation and better classification of most of the training observations. They are sometimes called soft margin classifier since it allows some of the observations can be predicted false. By this way, it can deal with the non-separability of the datasets. Let's remember the formulation of the support vector classifier. We are trying to maximize the margin, subject to constraints that are the summation of beta squares equal to 1 and yi times beta 0 plus beta 1 x1 plus beta 2 xi2 plus till beta p xip greater than or equal to m times 1 minus epsilon I for each I in our data. And also, each epsilon I should be greater than or equal to 0 and the summation of epsilon I is less than or equal to c. Remember that epsilon is the error measure and it is positive when the classifier classifies incorrectly. C is the non-negative parameter of the method. It can be seen as the budget for making incorrect predictions. As seen in the formulation, if we have c equal to 0, the method becomes maximal margin classifier. Support vector machines are the extensions of the support vector classifiers. The key difference is the use of kernels, which are resulted from enlarging the feature space in a specific way. The kernel approach that we describe here is simply an efficient computational approach for enacting this idea. The main idea of this extension is that we can enlarge the feature space in order to accommodate nonlinear boundaries between classes. When the formulation of support vector classifiers are analyzed, it is seen that only the closest data points to the separating hyperplane play a role in the optimal solution. Using this fact, we can use the inner product of observations to reach the optimal separating hyperplanes. Kernels are the generalized version of inner products that appear in the formulation of the problem of support vector classifier. Now suppose that every time the inner product appears in the representation, we replace it with a generalization of the inner product of the form k xi xj. Here k is some function that is called a kernel function. What is a kernel function? A kernel function is a function that quantifies the similarity of two observations. For instance, normal inner product can be given as an example to kernel functions. As you know, when we use the normal inner product function, this will result in ordinary support vector classifier. Let us give some examples to the kernel functions. The one that we just gave is called linear, as it is linear in the features. The linear kernel quantifies the similarity of a pair of observations using Pearson correlation. There is also polynomial kernel of degree d, where d is a positive integer. Using d provides a more flexible decision boundary. It increases the dimension so that the dataset can be separable easier than before. Another popular choice of kernels is radial kernel, which is defined as e to the power minus gamma summation of xi minus xj squares. Here, gamma is a positive constant. It works well in nonlinear decision boundaries. Radial kernel has very local behavior in the sense that Only nearby training observations influence the classification task. Until this point, the discussion of models are limited to binary classification. However, there are many real-world applications of multi-class problems. How can we deal with such cases? Well, we have two ways to cope them. First way is called one versus one classification. In this method, we are going to compare a class with each other so that we are going to compare all pairs of classes. Therefore, if we have k classes, then we need to train a model for all combinations of two classes. In the end, we will classify a test result by looking at the most frequently assigned one. The second way is called one versus all classification. This method aims to train a model for each class. This results in k different models, each specialized in classifying the related class. Each time a model compares one of k classes against k-1 classes. If we denote the values of a test observation as x1, x2 till xp, then we classify the test observation as the class where beta 0k plus beta 1k x1 plus till beta pk times xp is maximized. This means that we are assigning the test observation to the class where we have the highest level of confidence. Today, we have covered support vector machines. We formulate their mathematical problems and introduce the use of kernel functions. Lastly, we discussed the use of support vector machines in a multi-class classification setting. We would like to hear what you think about our content. Thank you for watching our videos. Please do not forget to hit the subscribe button. By doing so, you're really helping us to grow. You can always ask questions by leaving a comment below and we will be happy to answer it. In our next video, we will cover single-layer neural networks. See you in the next videos. Bye bye.